Okay, so time to get started. Here's where we were last time. We were talking about line integrals. And let me just remind you what a line integral is. So the idea is, I guess I'll come back a little bit further, that for whatever reason, we've got some curve, and we're interested in some computation that happens on the curve. Maybe we want to compute the mass of a rod that's bent into the shape of this curve. Or maybe it's in R2 and we're trying to figure out how much snow is accumulated on top of this driveway that follows a particular curve. Whatever the question might be. And so the idea is we take that curve, we chop it up into little pieces, such as that. And on each piece, the kinds of applications this is set up to address, we'll be looking at the size of that piece, namely the length of that little piece of curve, and multiplying by the value of some integrand. So whatever it might be, if you're interested in computing the mass of the rod bent along this piece of curve, then you're looking at density, mass per unit length, that you'd multiply by length to get the mass on each piece that you would then add up over the whole thing, etc. Okay. All right, now question, how do you compute these things? Well, I want to take a calculation that's done on this domain that I don't like because it's dimensionally weird, right? It's a one-dimensional thing in a three-dimensional world. It's a mismatch. It's not like any other kinds of integrals we've seen. We want to take this dimensionally weird domain and we want to view it as being the image of a nicer domain. Here we have a one-dimensional interval on the one-dimensional t-axis. This is a Calc 1 domain. Right? It's a much more desirable domain. And having found our undesirable domain as the image of a more desirable domain, we want to then do a pullback through that function to turn this undesirable integral into a better integral. And we worked out the details of that last time. We worked out the stretching factor. A couple different ways to see what the stretching factor was. Here's the kind of the quick and easy way. And that is distance equals speed times time. Right? If you want to know what's the distance you've traveled along a parametric curve, distance is speed times time. So speed, in this context of parameterizing a curve, speed is your stretching factor. Now, I came up with that same result, and morally equivalent result, here by invoking the derivative transformation. And the purpose of this calculation here is to observe that, hang on a second, I got my colors backwards. Let's see, purple, yeah. The derivative transformation is what allows you to take an input change vector and relate it to the corresponding output change vector. Let me zoom out. Right? So, you view this as being the change associated with a certain little tiny vector. This, the vector that sort of follows the curve along that little piece, call that the output vector. They're related by the derivative transformation. Now, we don't need this machinery for this particular case. In this particular case, look, distance equals rate times time. We already have that answer. Right? But setting it up in this way is going to be very useful in about 5 minutes when we get to doing the same thing in the next sort of construction. Okay. All right. The punchline was this definition of a integral. A line integral, what I like to call a scalar line integral. And that is this notation, this being the Riemann sum that we've been talking about. I want to take a curve, chop it up into little pieces, take the size, length, ds of each little piece, multiply by the value of some integrand, maybe density, whatever, to compute total mass of the metal rod or total volume of snow that I had to shovel or what have you. And we're rewriting that now as a pulled back integral on the t-axis. And this comes straight from that calculation we just did. Note that ds is speed times dt, just as we discussed. And in the integrand, all I've really done with the integrand is just plug in, right, that x is a function of time. Okay, so it's really a lot like change of variables, just in a different context, and a different formula for our stretching factor. Make sure to memorize this formula for the stretching factor. Speed, easy for everyone. Okay, so that's where we left off last time. I want to show you an example now. We need to, get our hands dirty. So we're going to go with the bent rod example because we already have agreed that the way you can compute the mass of a bent metal rod is by way of a scalar line integral like this. Right, so again, mass per unit length times the length gives me mass. I then add up all the pieces of. Okay, so now how do we compute this thing? Well, we're going to come back up to the formula we just motivated. Right, here we have a formula that says if you have an integral, scalar line integral, then you can pull back to a Calc 1 integral with this formula. Notice everything in this integral is in terms of t, so the very first thing we're going to have to do in this example down here is parameterize our curve. So let's do that first. Our path is the top half of the unit circle in R2. Let's draw ourselves a picture. Top half of the unit circle in R2. Okay, so we've got to parameterize that curve. Now, good news, this is a familiar curve. It's easy to parameterize. Right, different ways to go about justifying this. Probably the easiest way to get from this curve to this parameterization is to write this curve in polar coordinates r equals 1, and then we've solved for one of the variables. Remember, if you solve for one of the variables in terms of the other variables, you plug that in, and that gives you a parameterization. T goes from 0 to pi because top half of the unit circle. Okay, is everybody happy with the parameterization? Okay, so now it's really very plug and chug at this point. Let's compute our stretching factor. Here's our formula for our stretching factor. It's the magnitude of the velocity vector, aka the speed. Velocity is the derivative of the parameterization, which is easily computed like so. The magnitude, little Pythagorean calculation there, turns out to be 1. Very convenient. And here's how the calculation proceeds, and it's literally just a matter of plugging in. Density is a function of position. Position's a function of time. So density is a function of time. Comes from just plugging in the parameterization. So by which I mean specifically, let's see here. Let me highlight this a little bit better. So position, which is a function of time, cosine t, sine t. That's the parameterization that we have on the previous page. We're literally just plugging in our parameterization here. Yeah, everybody good? Okay. ds is speed times dt, and I missed the ds is speed times dt. We just computed speed. Speed was 1. Mm-hmm. So just a matter of plugging in. And, well, sure enough, we have ourselves a single variable integral. All I've done here on this density function, let's go back up and remind ourselves we were given the density function. Density is x squared plus 2y squared. So x squared plus 2y squared. I'm just plugging into the density formula. And yeah, single variable integral, plug and chug. And y'all can compute these kinds of integrals. So let me take that as an excuse to remind you again. So I'm assuming that you can compute these kinds of integrals. If you're a little rusty in your integration techniques, you definitely want to brush up on that. This calculus class assumes that you're proficient with these kinds of integrals and more. All right. So there's another example in here. I'm going to let y'all read this one on your own if you'd like, and several exercises, of course. And we're going to move on now to scalar surface integrals. This is a very, very similar idea to what we just talked about, scalar line integrals. It's just now suppose that I have a surface. Now, what kinds of applications might we be interested in talking about here? Well, gosh, there's lots of them. Maybe instead of a bent rod following a curve, maybe we have a bent sheet of metal. following some surface. Something like that. And for whatever reason, I want to compute the mass. So I argue that the total mass is the sum of all the little masses that you get when you chop it up into little pieces. That's just chopping up the surface, mind you. Let's recognize this is a dimensionally awkward situation. Again, kind of like a curve. In that the surface is a two-dimensional thing, but it lives in a three-dimensional world. Right? So triple integral would not be appropriate here. This is not an integral over a three-dimensional solid in R3. This is an integral over a two-dimensional curve in R3. Okay, so anyway, chop it up into little pieces. On each little piece, furthermore, let me come back up here to our definition. On each little piece, we're going to want to take the area of that little piece and multiply by the, whatever is appropriate to our application. Now again, maybe we're computing mass, and this is mass per unit area, which, think about it, mass per unit area times area would give you little pieces of mass that you want to add up over the entire surface. Or, hey, maybe this surface is just covered with ants, right? And I know ant population density, number of ants per unit area. And I want to compute the grand total number of ants. Well, okay, so ants per unit area times area gives you ants on each little piece, and you add up all the ants on all the pieces. Okay. Point is, on a domain like this, there's plenty of situations, plenty of applications that I would organize the calculation of which by the same construction. Sum integrand, appropriate to the application, times area gives you the answer on each little piece, and then you add up over all the pieces. Okay, so this algebraic construction comes up a lot. There's a Riemann sum. This specific one, we denote like that. Again, I think this is really plausible notation. We're shorthanding delta S by ds. You probably would have guessed that, right? This is a summation that's happening over a two-dimensional surface. So you gotta have to tell me kind of two things to describe where you are. You know, which of these slices are you in, you might say. And then, once I know which slice you're in, I would need to know which little piece along that slice. Two indices. So, two indices, we're going to shorthand it with two integral symbols, just like a double integral. Okay, so this notation in mind, here's how you compute the mass of a curved sheet of metal. I mean, this was our motivating example, right? So the grand total mass is the sum of the little pieces of mass that you get when you slice that up into little pieces. On each little piece, mass per unit area times area. So here we have a Riemann sum that should, if we can figure out how to compute these things, a Riemann sum that should tell us the amount of mass on the piece. All right, now before I go on, does anybody have any questions about this so far? The looming question, of course, is, yeah, this is nice notation and all, and good for you for having a strategy, but how in the world are we going to actually compute these things? Okay, so the way we compute these things is by way of a strategy pretty similar to line integrals, right? What was it about line integrals? What was our approximate, our broad brushstroke strategy for computing line integrals? Well, we decided to recognize that it was a domain that we don't like, and we parameterized, because parameterizing takes the domain that we don't like and views it as an image of something that we do like, and then we did a pullback. So we managed to, by finding it as an image, we were able to take an integral whose primary annoyance was that it's dimensionally weird, and I was able to pull it back to an integral on a domain that's not dimensionally weird. So we're going to do the exact same thing here. I'm going to try to view this surface as being the image of a domain that I like better. And I like rectangles in R2. Right? Rectangles in R2 are easy domains. That's double integrals, iterated integrals. I mean, it's section 5.2. Right? It's a long time ago. We're experts on how to do these kinds of integrals. So I would like to view my surface as an image of one of these domains, then I'm going to take my undesirable integral, pull it back to a more desirable integral. Okay, so here we are again. We've got to figure out the stretching factor. Now, here's how I'm going to do that. I'm going to take little pieces of area over here in the UV plane, and I'm going to ask, what is the image look like? Now I appeal to your intuition that this being a little rectangle, this is going to be some sort of a stretched out rectangle, so namely a parallelogram, approximately. Not exactly, it's not exactly flat, but it's going to be parallelogram-like. Right? And how can I understand this parallelogram? Well, I'm going to first talk about the little edge vectors in here. Talk about that little vector defining the bottom edge of the rectangle, this little vector defining the left edge, and then I'm going to talk about their images. All right, we'll talk about what is the image vector there, what is the image vector there. All right, if I understand these image vectors, then I say, hey, this is basically a parallelogram. I know the two vectors that define that parallelogram. I'm interested in computing the area of a parallelogram, and I know the two edge vectors. We have formulas for that. Okay, so it's a kind of a familiar situation. We have a couple of input vectors. We're interested in knowing their output vectors. And input vectors and output vectors are going to be related by way of the derivative transformation of the function in question. So just like in the case with parametric curves, by the way, just like in the case of change of variables, we're going to be interested in applying the derivative transformation to a couple of vectors. Okay, so that calculation is, I passed it up, here it is. So our input vectors, I claim are E1 du and E2 dv. Let me find where do I have that? Yeah, here we go. Whoops. Yeah, right. There they are. E1 du, E2 dv. Now, just to be clear, why is this little blue vector here E1 du? Well, it points in the u-axis direction. That's in the direction of the vector E1. And this little piece of area, this being the u-axis, this little piece of area has width du. So the vector I'm looking for is a unit vector, it's a vector pointing in the direction of E1 and whose magnitude is du, therefore it's E1 du. And likewise, that's E2 dv. Okay, so those are our input vectors. We plug those into the derivative transformation. And what comes out then will be our output vectors. These vectors I'd like to compute. The edge vectors are, what do you get out of the derivative transformation? So this calculation gives us what we need. And now these calculations here are, this is just reminders of certain facts we already know. We know that scalars can pop out of velocity vectors. Right? And we know that directional derivatives, unit directional derivatives, where your velocity vectors are standard basis vectors, are partial derivatives. So xu and xv. They're just the u partial and the v partial of our function. So there we go. And by the way, this might look familiar. Xu du, xv dv. We wrote down something almost exactly like that when we were doing change of variables. I think it's a really instructive exercise. I encourage everyone to do this. Look at this calculation here, and then flip back in the book to where we did something kind of along these lines with change of variables, and you'll see they're morally identical calculations. Okay, so XUDU, XVDV are these vectors. So, like this. Oh, see, I have to zoom out. So, XUDU, XVDV. Now, keep in mind what we're interested in. We're interested in this little piece of area. Right? The area of this kind of sort of parallelogram-ish bent little shape, piece of a surface. It's not exactly this parallelogram, but come on, in the limit, it's going to be well approximated by that parallelogram. That parallelogram has an easy area to compute. Its area is the magnitude of the cross product. The magnitude of that cross product, XUDU cross XVDV. Okay, so that's right here. Let me zoom back in. So the area we're interested in, magnitude of the cross product, right? XUDU cross XVDV. That's the thing we're interested in. It's all algebraic games from here. The DU factors out, the DV factors out. I hope that looks familiar. We did something exactly like that in change of variables. Same situation, really. I mean, in that case, it was a determinant instead of a cross product. But again, the scalars factor out for, morally the same reason, just different algebra. Lo and behold, we're done. Here we go. We have a formula that gives the output area as something times the input area. Namely, we have here a formula for our stretching factor. Our stretching factor. You just got to memorize this formula, by the way. You just have to memorize it. The formula for the stretching factor is it's the magnitude of the cross product of the two partial derivatives of your parameterization. So make sure to memorize that. By the way, that vector comes up a lot. So we've given that vector a name. The vector on the inside here. Let me highlight. The thing whose magnitude is the stretching factor. It ends up being important in other contexts. Not to mention, it's convenient in this context to be able to write it a little bit more succinctly than this whole cross product formula. So capital N is the name that we give to it. Okay, so the magnitude of capital N is our stretching factor. Okay, and that calculation having been done, now we have a theorem on how to compute surface integrals. Let's see here. I'll use purple. Here's our theorem. Here's a surface integral you might want to compute. Now again, why do you want to compute a surface integral? Maybe you want to compute the mass of a bent sheet of metal, or maybe you're counting ants, or whatever reason. There's an integrand appropriate to the application. And given that you want to compute a surface integral, the pullback, it's kind of analogous to what we did in the case of a line integral. We just plug in that x is now a parameterization. In the case of a line integral, x was a function of t. Here, x is a function of now two parameters because we parameterize the surface. So x is a function of u and v. Punchline, plug in the parameterization, right? Is exactly what you would hope it would be. Just plug in the formula for the parameterization. It's distracting. The ds we just got through computing. Right, ds is magnitude of capital N times dA, magnitude of capital N times the area for the pullback area of the UV plane, so the UDV. And off you go, plug and chug. Here's our mysterious 2 2-index surface integral that we just got through defining. And here is a plain old garden variety double integral in terms of u and v. Okay. And I want to repeat again, very nice to notice that everything in here is in terms of the parameterization. Here we rewrote f by plugging in the parameterization. The stretching factor that we computed here, that stretching factor comes from a cross product of partial derivatives of the parameterization, right? It's x, your parameterization that you take partials and then a cross product and then a magnitude. Okay. So everything comes from the parameterization. First step, therefore, in doing any one of these kinds of problems is to do a parameterization. Okay, so here's an example. Again, I'm going to use our motivating example of a metal sheet. And let's compute the mass of this metal sheet. We're given a formula for the density, mass per unit area. Right, it's this formula of position, z squared. Right. And what is our surface? Our surface is the graph of this function here over the unit disk in the xy plane. So now, very important. Right, remember I'm using this word graph here. This means it's, that's a specific surface that you get from applying a specific process, specific construction to this function f here. Okay, so how do we parameterize a graph? Well, the graph parameterization, real handy way to parameterize a graph. My favorite way to parameterize a graph. Note that the parameters are the first two variables, x and y. And then the function tells you what the third variable has to be. It's our usual graph parameterization. Right. Special case of the more general idea we talked about again a long time ago of if you solve for one of the variables in terms of the other variables, then that motivates a parameterization. And here, notice when you're looking at the graph of that function, the graph is z equals. That's what graph means, right? Z equals. And so I have solved for one of the variables in terms of the other variables. Okay, so having our parameterization, now we're just going to follow the rules up here. The rules say we're going to take our parameterization, take partials of it with respect to the parameters, take a cross product to get our in vector, and then take the magnitude. Okay, so here we go for our parameterization. The partials, there's the partials. And it's just partial derivatives of the parameters. I mean, it's straight up calculation, real easy calculation, right? Plug and chug. The cross product, that cross product